too much fun today. Okay, let's go for it, huh? 终于，米团优选又可以送货了，哈哈哈！开始挑啊！我发现我这2本书，这一本还有那一本，包含了很多我研究生 master degree 要学的内容，有体力学、材料力学，所以说这里面所有的我看看，钢结构我学不了，电工学我自己学不了，别的我后来都得学。还有什么工程经济？对，吧，开始吧。这学期毕竟3门课还是简单，上午把那啥上了。我发现开始直播好像这个网速会受影响。
What you mine out of material, out of resource is reserve. And so
的确是，我一开直播的话，这地方就没法学了，我就看不成视频了。操了个蛋！真他妈垃圾！这他妈怎么办？我他妈直播看书。
the reserve is always smaller than the resource.
我操！对吧？我直播看书算了。
And you don't mind it because of the physical constraints, the mining method, and such like, and economics. So the economics might say that this little bit of whatever the geologist has put as the so-called ore body is not profitable. We won't mine it at all. We might go back and mine it later or go out of the ground, but the open pit we might not mine it. So I was struggling yesterday because I was tired about some of the various stages in the mining design. We actually start with conceptual design, and it's normally within 100% accuracy, plus or minus 100%. It can take up to, say, 1 month. Okay. Scoping study is more accurate, obviously, with plus or minus about 50% accuracy. And that we see what we could actually be done at that deposit. So yeah, we're moving on the scale, moving up the chain, and working out whether the project looks encouraging or not. Of course, you have to compare it with other projects. You choose the best project obviously first, we'll do the best project first, and that's why we have these stages. So we have these stages because if you know which stage you're at in the process of design, you know what the accuracy is, I suppose, the uncertainty is, and you can compare multiple projects together and work out what's the best way to proceed. And that's usually done in 2 to 3 months. And then it takes us to a pre-feasibility study, what should be done, and then a feasibility study. And the pre-feasibility study takes about a year, and then the feasibility study is usually over a year. And a feasibility study says what will be done. So what we will be doing. So it's more concrete. There's nothing legally binding you to any of these steps. You can jump steps if you want, you can miss them out. You don't have to do them. But it's advisable to do it initially, especially the pre-feasibility and feasibility studies. Because that will tell you exactly if you are going to proceed or not. And the more you go down in this list, the more accurate it becomes, and the more you know about the deposit. So then you have EPCM, which is an engineering, procurement, construction manager. To work out what you're actually going to do, what equipment you have, all the nuts and bolts, all the buildings, all the infrastructure. It's the real design work. So it's even the civil works on the surface. You have to get it done, and that takes us down to about plus or minus 5% error. Okay. So at every stage, you'll be thinking about an environmental impact statement, or EIS. You do this right at the start, and it's foolish not to do it from the beginning. There is an example of this in the I believe, where Rio Tinto wanted to expand or like create a new iron ore mine. It was going to cost them about $6 billion to expand. And the government says after they presented what they wanted to do, the government said you need to do an audit on all of the plants and animals, count the number of plants and animals, and identify the plants and animals in that mining area. And so they did. They found there was some underground spiders in the area, and the government says, okay, hang on a minute, these are not found anywhere else. These are new species to us. You cannot be mining in that area now. So Rio Tinto took about 6 months to look around the Pilbara and said, okay, well, actually, not only here, but elsewhere around the Pilbara. And went back to the government and said, okay, we've got these spiders everywhere, can we start mining? The answer was yes, obviously, but that was 6 months delay. So that's a good example of why you want to start that process early and get the ball rolling, so to speak, in the environmental impact statement. Yeah, so it costs them a lot of money and delays to start the mine. So this graph shows the level of accuracy in, I suppose, chart form, graph form, per study site over a number of years. Okay, so note that there's different terms involved with this: scoping, preliminary feasibility, bankable feasibility. That's just probably pre-fees, that's feasibility, and then we've got the EPCM, that's what we've put before, and then operation, and of course scoping. So there's different terms for different countries. This might be from America. I'm not sure exactly where I got from. Yes, American. There might be different terms, so just be aware of slightly changes over it. So what this is showing is the first stage has a lot of uncertainty. And then you get down to a level where you're operating and you know exactly what you're doing and not a lot of uncertainty at all. And note that this process is not always continuous. You might do the scoping study for half a year, then stop, and then pick it up later because you've looked at a different project, or better to spend your time on a different project, and you continue on. So it normally follows that kind of trend. This is showing a similar thing in terms of relative ability to influence cost. So the amount that you influence the cost of the project will determine how much profit you'll make out of it. If you reduce the cost more, obviously you'll make more money. So in the design phase, if we go surface and underground, can make a huge difference to the cost. But once you start mining, it's normally a lot harder to change. This is true for most engineering projects. We design well at the start. We do a good job of design work, and we don't rush and do it because we might find a different way. We want to plan as much as possible. For example, in another field like automotive engineering or mechanical engineering, further might make a decision about what type of car they want. And so once they build it, they can't really change anything to make colors of it. So so we want to make better informed decisions earlier and reduce the cost and the profitability. So the initial decisions you have to make at a mine. First of all, you have to do a risk assessment on it, especially for things like like location, as I was showing you before, where you are in the world, so also is it sovereign risk or all those risk categories that I showed before. We have to worry about the production rate. Gold, you double the production of gold in your mine. It's not going to make much difference to the price, but other commodities, for example, copper and lithium, if you mine and flood the market and produce more material, the price will change. You have to be aware of that. And because of other mines mining at a certain production rate, you have to be mindful of what the current production rate is for the world or your country, and so you don't flood the market or and drop the price too much. So the bigger the mine, the cheaper it is normally to mine. We normally have larger equipment, which means that it's cheaper per ton. This is not always the case. The best way to mine is the largest possible mine you can do, obviously, but there is a tendency for mining operations nowadays to do this. We do go underground on mining with open pit. We do go underground. We've got technical considerations to worry about, and this depends on depth to a certain degree. Obviously, surface is cheaper per ton, and this is mainly because the equipment is bigger. In surface mining, we have trucks that are about 363 tons, metric tons, and the biggest underground truck is about 60 tons. So there's a huge difference in terms of capacity of underground and surface. Note, I talked about that a little bit before, but you can have both. You have a surface mine first, and then go underground as the ore deposit gets deeper. But once you start, it's very hard to change the mining type, apart from going from surface to underground. Okay, so the design is an iterative process. You've probably done some design work hopefully before, and you will be doing that in civil and mining as well. You certainly won't design a mine and then come back to it 20 years later and see how it went. It's a very silly thing to do, and no one does it. It's an ongoing process, basically. So you always make changes along the line because of price, cost, production rates. You might not be meeting production rates. The cost might change. The price fluctuates a lot, and you rarely receive the correct answer from your design. So what you do in reality is not always the case of what you design. So be aware of that. And in reports, it normally says that there's an optimistic or pessimistic view, or there's risk associated with that, or a best guess case, or best option, and you pick what you want to. Let's say that's a financial report, and you want to invest in the company, then you pick what you think is the most likely case to go forward. So it's better to be pretty right than precisely wrong as before. So we want to be as close as possible to the answer, but we don't mind a bit of uncertainty, especially in mining. So you have a lot of uncertainty in engineering projects. You might be aware of that. So for example, interest rates, inflation, capital costs, power costs, labour costs. And for mining, especially, commodity prices is a big factor. A lot of uncertainty comes from commodity prices, because we can't predict what's happening in the future. And there's extra uncertainties for the raw materials. So unlike a bridge, say, that we might want to order a part in to get up to exactly, within plus or minus 1% strength, and we might want that at 100 megapascal strength of whatever it is, a girder or a beam or something, then we know that we're getting that kind of material, and we know the strength. But in rock, we don't know what that strength's going to be. We don't know what we're going to encounter underground, and it's highly variable depending on different areas, depending on geology. And this adds an extra layer of unknowns in mining just because of the geology. So for designing the mine, the days where we just came along and dug a hole and found some gold are largely gone. So we don't find like visible gold anymore. We can't just go in and say, okay, that was good on the surface, down and see what we find. Most mining companies seek larger tons because this is a cheaper way of doing things. Means they can mine lower grades at profit and reduce the risk by having huge reserves which they mine. So it's better to have a bigger deposit, you spread your risk over a bigger deposit and have lower grade than a high grade deposit with more risk or uncertainty. So 130 years ago or 150 years ago, people were throwing rocks away with gold below $20 grams per ton if they could not mine that at a profit. Today that's a fantastic grade for gold. So we would say thank you very much. We'll take that gold, thank you very much, and mine that material. So advanced technology has meant that we've been able to mine lower and lower grades, and in fact we might want to go back and mine the gold that's over in the mine or on the surface in waste after whatever we want to do. So today a gold ore of about 0.7 of a gram per ton, which is 0.00007%, can be mined profitably. Just keep note of that. So we're going to go through, so mining requires a lot of scientific technology now. It probably didn't as much in the past. So we're going to go through what a mining engineer wants, the main purpose of a mining engineer, what we want to happen in a mine. First of all, we want the best economic return through extraction of the resource. Of course, being socially and environmentally responsible and being very safe in the way we do it. This involves choosing the mining method, working out how fast you want to mine it, the production rate, whether we're going to mine it very fast and do it in one year, or do it over, say, 2 years. We want to minimise the payback period, which is basically the amount of money that it takes to pay back a loan or investment. So normally mining uses loans from the bank, it's very safe, and the banks want their money back as fast as possible. So things will go wrong in your mine, so they want it as soon as possible. So if you say that you've got a 50-year payback period, the bank might not want to give you money, it takes 29 years to get paid, opposed to something that's like 5 years or so you get paid more faster. And so therefore you're constantly monitoring performance of your mine and adjusting it where necessary. Mining engineers are normally if you don't specialise a jack of all trades, a master of none. You need to know a lot of technical stuff. So that being like engineering work, like even civil, electrical, and also economics, because we're dealing with making commodities and geology as well. Get to know a little bit about geology as well. So we know a lot about a little few subjects today. And yeah, so it depends on what sort of specialisation you get into or what career you want to do, get involved. So we also want safe conditions, obviously no one getting hurt. We want low development costs up front, so we don't have to borrow much money. Short time starting the project and processing ore because you only get paid once you produce that commodity. So we want a short lead up time. There's a high degree of mechanisation in Australia because of high labour costs. And because mechanisation is generally more reliable and produces more. We need big machines that are reliable and we don't have to worry about humans doing a lot of work. And that's the same with automation. We use it as appropriate. A lot of trucks in the field in the last 10 years or so are automated, they don't have drivers. Automated trucks are better, sometimes better for making decisions, and they don't get fatigued from the machines. The equipment is very expensive, so you want to use it as much as you can, so that means you want to be using it every day, 24/7, depending on how much you want to service the machine. So there might be a backup of the machine, so you need a backup, but you're always cycling through the maintenance process doing that. We want a high resource recovery, so we want to get as much ore out of the ground as we can, and of course we want to be environmentally sound, because we won't be mining in the future if people think that we're not doing it correctly, and mining environmentally well. So I'm going to step through some definitions. I've talked before about tons, okay, so these are some very basic definitions. Tons come in very small. The one we use is metric tons. This is 1,000 kilograms, or 2,205 pounds. and that is the main one we use. Okay, so if I talk in tons, I'm usually using the metric tons. What's confusing is in the US they use short tons, which is 3,000 pounds, which equates to 907 kilograms, and this is usually quoted in trucks. So they quote in short tons because it looks like they've got a bigger truck. So if you've got 400 short tons or US tons, it sounds better than having a 353 ton truck in metric tons. This was that. And some of the equipment is going to be made or designed in America as well. So, and then there's also a UK, a long ton, that's not very common these days, which is 2,240 pounds, and it's closer to the metric ton. There's about 1.6% difference. Just be aware of this if it comes up, and beware of units. So an ounce in condition is 28 grams, whereas we use a special ounce in mining, which is 20 ounces, as I mentioned before, which is about 31 grams. We use this to weigh or measure our precious metals, and there's about 10% difference between the two. I'll talk about the truck. That's the largest truck in the world at the moment. And I've talked a lot about ore. I have to give you the definition of that because that's very important. We're mining material. We have to know what we're doing. Ore is the assembly of minerals or rock containing enough material to economically important minerals or elements or compounds that can be extracted from assembly and sold at a time, at a place, at a profit. So what you might notice in that description or that definition, which you can read yourself, is that we mentioned profit, and economically, for profit is definitely not a geological term. It's what we can get out of the ground and sell it at that time, at that place. So depending on the country you are, time is right now, and sold at a profit. Obviously, revenue is paid by selling the minerals, and is not, you want it greater than the costs of extraction. Yep. And what classified as ore can be vary according to changing criteria. It might be that you can see it very well on a mine. You might have a white streak of quartz with gold in it, and you know that's the ore body. But most of the time it isn't as deep up. So you have to know it's not just based on colour or shape or whatever you're looking at. Okay? So it's always changing because the price changes all the time. So the amount of money you get through changes depending on how much you're mining, and the new low-cost mining techniques might come along, and you might want to mine it in different ways. So ore is a changing thing. So it changes depending on where you are in the world, where you are in the state, or whatever, what kind of geology you have, and it's based predominantly on economics. It is not a fixed geological, or it's not based on geology as much. It's not a fixed geological definition. Okay, does that make sense? We understand what ore is. Basically, a concentration of minerals that can be mined, processed, and sold at a profit. So the next one of definitions I'm going to talk about is something very simple. So we're going to talk about base cubic meters or BCMs. A base cubic meter is a material in the ground measuring 1 meter by 1 meter by 1 meter. So a cube of rock sitting in situ in the ground. It's pretty straightforward. It has a bulk density or in situ density in terms of tons per cubic meter, and it's the same as grams per centimeter cube. Same number basically. Okay, because that's straightforward. But the thing is, once we blast the material, we cut the material, whether we're doing the digging material out of that coal, or we blast the material with hard rock, the material swells and the density drops to much air in this material. So if you dig a hole out anywhere in the soil and put it on the side, you try and put it back into that hole, you're not going to fill up that hole as much. So you're going to let over material. The only way you can get back into the hole is by vacuuming it, by jumping on it or using the shovel. And that means that we've fluffed up or aerated the material. Rock does the same thing. It swells, and we call it the swell factor. Okay? So it has the same weight, obviously, because we've got it's still the same material, we haven't lost any mass, but we have more volume, so the density decreases. So the volume from what was in the ground usually goes to about 20 to 30% of the original volume. We call that the swell factor. So we've got 1 8 cubic metre or BCM in the ground. We'll swell it if there's a 30% increase in the original volume. The swell factor is 30%. We have 1.3 8 cubic metres when we mine it. Yeah. So this is important because we're using that to using the volume of the rock in our machine. So we have to do this. We know.
你他妈操你干嘛？
Okay, let's convert it directly. But the thing is, once we blast the material, we cut the material, whatever we're doing, we're digging the material out as coal, or we blast the material with hard rock, the material swells and the density drops. We introduce air into the material. So if you dig a hole out anywhere in the soil and put it on the side, if you try and put it back into that hole, you're not going to fill up that hole as much. So you're going to let go of the material. The only way you can get back into the hole is by compacting it, by jumping on it or hitting with a shovel. And that means that we fluffed up or aerated the material. Rock does the same thing. It swells, and we call it the swell factor. Okay? So it has the same weight, obviously, because it's still the same material, we haven't lost any mass, but we have more volume. The density decreases. So the volume from what was in the ground usually swells to about 20 to 30% of the original volume. We call that the swell factor. So we've got 1 8 cubic metre or BCM in the ground. We'll swell it if there's a 30% increase in the original volume. The swell factor is 30%. We have 1.3 8 cubic metres when we mine it. Yeah. So the swell factor is 30%. We have 1.3 8 cubic metres when we mine it. Yeah. So this is important because we're using that to using the broken rock in our machine, so we have to know what density it is. We know, yeah, we're going to take a certain amount of volume, right? So it's very important. I'm going to go through an example. I'm going to get you to calculate it very simply. There's no tricks with this, okay? So please try to do on the calculator on your phone. Put the calculator on your phone. So we have an in-situ density of 2.5 tons per cubic metre and a swell factor of 25%. What is the loose density? Can anyone tell me what the loose density is? The loose density is from after the swelling has occurred. Can anyone calculate for me? After we mine it?
不对，
Give you a number.
除以2，
It's not hard, don't be afraid of getting wrong either. It just shows your reason. Yes, you're right. How did you do that? Yep, because you've gone from 1 8 cubic metre, you've increased it 25%, so we've increased the volume by 25%, so you now have 1.25 cubic metres. You have the same tonnage, so we've still got 2.5 tonnes. So 2.5 tonnes divided by 1.25 cubic metres gives you 2 tonnes per cubic metre. It is very simple. There's not many tricks in mining in terms of that kind of stuff. We're not talking about rocket science here or brain surgery. These calculations are fairly simple unless you get into things like rock mechanics and specialised fields. Then it gets a lot more technical. But this is obviously the introduction to mining, so we want you to set through the basics. So the other thing you have to be aware of is selectivity. Selectivity is the ability to mine precise geological boundaries. So it depends on the size and shape of your mining unit. So if you have a mining unit that's this size, say this cuboid or rectangular shape, you fix that shape. It's the lowest, smallest shape you could get to mine that material. And therefore, your ore body might run through it, or your mineral zone might run through it, and you still mine that area though. So you mine this overall area. So that means that you'll get dilution, and dilution is the amount of tons of waste material unavoidably mined together with the ore and sent to the processing plant. So obviously you want this as low as possible, and depends on the mining method. So if you have smaller and smaller selectivity. Like you're getting more selective with your mining method. Might mine down to teaspoons, for example. Something silly. Mining teaspoons, you can get right down to the ore and you'll have less dilution. You fix that shape. It's the smallest shape you can get to mine that material.
操你妈逼！
And therefore,
干你妈一回！我操了！
your ore body might run through it, or your mineralized zone might run through it, and you still mine that area though. So you mine this overall area. So that means that you'll get dilution, and dilution is the amount of tons of waste material unavoidably mined together with your ore and sent to the processing plant. So obviously you want this as low as possible, and depends on the mining method. So if you have smaller and smaller selectivity, like you're getting more selective with your mining method, might mine down to teaspoons, for example, something silly. Mining teaspoons, you can get right down to the ore and you'll have less dilution. Dilution is around about 10%, depending on which mine you are in. It's a normal assumption that you make, and depends on the mining method, obviously. So if you have underground or surface mining, it'll be different a little bit. So it is expressed as a percentage of ore tons. So if you have 10% dilution, it means you mine 1 ton of ore and you'll mine 0.1 tons of waste. Waste per ton of ore in percentage. And it includes unplanned dilution as well. So you might have a mine or stope design or whatever you're mining to try and get out of the ground. You've defined the area. This is what we're going to mine, but it actually extends further than that, and you get overbreak in a stoping situation. You'll have more dilution. So we include this in the dilution in our calculation. So it's planned and unplanned dilution come added together to create this chemical solution. Does that make sense? Yep, pretty straightforward. But we have to make these definitions clear. So mining recovery is the percentage of ore sent to the processing plant. That is, so the percentage of ore sent to the processing plant. So some mining methods leave behind ore, especially in underground mining. You might want to leave for support and for openings. Certain places where the ore has to stay there, and it's normally measured in percentage. So we.
你他妈死了！我操！他妈结束了！我操你妈！ 真的他妈的垃圾！哎呀，我现在怎么办呢？我去冲杯咖啡去。这个怎么喝？真他妈的垃圾！妈的，一个sample都没完呢，我操了！ 60分。For each scenario, calculate the amount of gold delivered to the processing plant and the amount of nickel contained within it. 我上哪去弄20%的？哎呀，我他妈的去冲个饮料去，冲杯咖啡去。哎，干嘛？你的可 TBT 啊，对对对，什么？TBT to match precisely precise your logical boundaries on dilution. Dilution 的意思是 the tone of waste material unavoidably mined together with the odds and sent with it to the lab to the lab expressed as 百分比 of the all tons e.g. 10% dilution 0.1不，soga 100的话，那就是10的6次方吨。它的1%的话是4次方。它是20%乘什么？操你妈！ 这还是个小病吧。 怎么着吧？哎，完活儿，滚！还出不来，你妈呢？啊 ，Lecture One， 应该是废掉了。8月2号，周一，操！我都看完了，去年的。
那我建议看的用国家。
This is textbook. Jim. Let's actually know association. I used some of the textbooks, but lecture notes. It's quite a substantial set of lecture notes. They are on LMS from the last year. Some of them will be changed. They will have mark 2019. There are few corrections. Okay, that is the unit organization. Any questions about it?
I can't understand your word.
If not, then let me proceed to the next. Let's change it introduction. So, today everything is simple. So in the introduction we will discuss what is rock mechanics, some examples, etc. Okay, we'll start with definition. Mechanics, or mechanics of geological materials. Traditionally, geomechanics includes two parts, rock mechanics and soil mechanics. I don't know why in Australia, when people say geomechanics, they understand soil mechanics only. In a country where mining is one of the great influences, it's a little bit strange. Mining requires rock mechanics. No. Rock mechanics is a branch of mechanics.
哎，我这个受不了了，我操！先关了，先关。真受不了，说的什么玩意儿？我靠！